Okay, this lecture is going to be a re-record of the lecture we had on Thursday, September 4th. And basically, I'm just going to go back and re-record the lecture to make sure that we simplify what we did in class to make sure it's more clear for you to see if that can clarify some of the questions and confusion that some folks might have had. So we remember that because of the periodic table being an arrangement of the elements that show predictable patterns in a periodic trend, we can look down a group or down a family and be able to, based on the number of valence electrons, be able to predict what types of properties they have. And some of the most noteworthy um, groups or families are the alkaline earth metals, which have 2 valence electrons, the halogens, which have 7, and the noble gases, which have 8. The noble gases have 8 valence electrons, and this makes them especially non-reactive because the shell is completely filled in their valence. Their valence shell is completely filled. So that means that there are no unpaired electrons that are available to participate in any types of reactions, so they're particularly non-reactive. And the alkali metals are another group that have some very predictable properties. They all have 1 electron in their valence shell, which means that they can lose an electron very easily to form a cation. And this is something that is common with all of the elements in that series, in that group. Similarly, for the halogens, they all have valence electrons that number 7, and they all can easily gain an electron to form an anion. And that makes them have some very special properties which are similar. The reason that we're looking at this is just to remind us that the periodic table is a grouping of elements that can show some similarities, and it can be able to predict the trends that we can expect to see looking at elements in the periodic table going across a row or up or down a group. So the trends that we're going to see, some of them can be explained by remembering what we talked about last class about shielding and penetration. Remember we said that the amount of charge that an electron is able to experience can be modified because of penetration or shielding. So the effect of shielding is going to play a role in some of the trends that we're going to see, including the size of the electron, how easy it is to remove an electron from its valence shell, how easy it is to gain an electron, etc. So what it is that happens when you have shielding is in your nucleus, whatever positive charge that you have is surrounded by a cloud of electrons of negative charge. So this cloud of electrons of negative charge that is closest to the nucleus are the core electrons. So the electrons that are closest to the nucleus, the core electrons, are the ones that are more effective in shielding that positive charge. So the core electrons providing this shield then prevent any electron in the valence shell from experiencing the full effect of this positive charge. So this electron out here is not going to be drawn as strongly toward this nucleus because there's other electrons out here that have negative charge that is preventing this from occurring. So this brings up the definition of effective nuclear charge. So the effective nuclear charge is the amount of net positive charge that that electron is actually experiencing through that cloud of electrons that surrounds the nucleus. It is defined by Z effective is defined as the number of protons in the nucleus of positive charge minus the total number of core electrons in the atom. So looking at an example, I think we looked at in class, we looked at oxygen and fluorine. Oxygen has 8, atomic number 8. If we take its number of protons, which is Z, I think that's the letter we use. Yeah. If we take 8, which is the number of protons in its nucleus, minus S, which is the number of core electrons, and that's 2, based on its position on the periodic table. And if we need to write this out, 1s, 2p, 2s, 2, 2p4. So a helium, 2s, 2, 2p4. So that means that the number of valence electrons here is 6. But these are not the electrons that we're concerned about. The number of core electrons are the ones that we're interested in, which is 2. So that gives oxygen an effective nuclear charge of 6. If we go across the row and do the same thing for the element that is right next to oxygen on the periodic table, which is fluorine, which has a effective nuclear, has a 9 as the atomic number. 9. But at the same time, looking at the electron configuration, these are just 2 different ways to write the electron configuration, remember? So looking at the electron configuration, these are valence electrons here, still only have 2 electrons in the core energy levels. So now the effective nuclear charge of fluorine is 7. So in the periodic table, as you go across, in the p blocks especially, S and P block especially, the effective nuclear charge increases because the number of valence electron, the core electron value stays the same each time. As you can see, if we were to go up to neon even, the valence electron, the core electron value stays the same. And so we're increasing in number. So oxygen is here, which has 8. Fluorine has 9. Neon has 10. I apologize. So oxygen here would have an effective nuclear charge of 6, 7, and 8 for fluorine and neon. So we can see that how that trend increases as we go from the left side of the periodic table to the right side. It increases in positive charge because the number of core electrons that we are subtracting from that positive value for the nucleus stays the same. So looking at the trends, there are different ways that we can look at measuring the size of an atom. The size of an atom is related to atomic radius. And we can measure atomic radius by either taking two atoms and sitting them side by side next to each other and just letting them touch each other, and then looking at the distance between their nuclei, or, and that's called the van der Waals radius, or we can look at the bonding radius. If we have two atoms that bond with each other, we can look at the distances between their nucleus when they're bound. Okay, so the van der Waals radius is when you just sit them next to each other, and the covalent radius is when they're actually bound together. So you know that radius from your math classes deals with the size of an atom. So we can look at the trend in the size of an atom. And so basically, this graph, I probably should have included this in the slide. But basically, this is from your book, and all it's telling you is that in the periodic table, the atomic radius decreases as you go from left to right. So the elements on this side of the periodic table are going to be larger in atomic radius than the ones on this side. It also tells us that the atomic radius increases as we go from top to bottom. And the reason that this is based on the effective nuclear charge. As you go, as we see in the next couple of slides, as you go from left to right, we just saw, using oxygen, fluorine, and neon as examples, we just saw that we increased our effective nuclear charge for each one of those elements as we went across in the periodic table, 6, 7, and 8. We see that the effective nuclear charge increases. So that effective nuclear charge actually is the charge becomes more positive, then it's able to attract the negatively charged electrons more strongly. And as it does that, then that means when you go across, there's a stronger attraction for those electrons. That means the electrons are more tightly pulled toward the nucleus, which means that the size of the atom gets smaller as you go in this direction. On the other hand, as you go down, we go to another completely different, completely higher energy level, which means that we have another shell, another completely higher energy shell that is occupied. So occupying a higher energy level means we have more electrons there. That means the electron cloud is bigger. So going from here to here, we get bigger. But within each period, the amount of electron attraction toward the positive nucleus increases as you go across. And so you end up getting smaller as you go from left to right. So I'm going to do small to large in a row and small to large in a column. Okay, so this is the trend for atomic size when it comes to the periodic table. Smaller things are on the right side and toward the bottom. Did I just say that? Forgive me. The smaller elements are toward the right side and toward the top. And all of these things here are just more detailed explanations of what I just said for the reasons why the electrons cause the atoms to be smaller or larger, depending on where they're located. Same for here, just a repeat of what I just said. So looking at examples of a comparison between um, pairs of elements. Let's look at some examples of how we can look at that periodic table and predict. We're going to find some examples here. The ones that we do first. All right. Atomic size. What is the largest atom in each pair? So, nitrogen or fluorine. Looking at it on the periodic table, fluorine sits to the right of nitrogen. So atomic size increases going from right to left. So therefore, we expect our nitrogen to be larger. Looking at another pair, carbon or germanium. If you look at the relationship between the two atoms on the periodic table, they sit in the same column, with carbon sitting 2 spaces away from germanium. And so we know that going down within a family, the larger atom is toward the bottom. So based on their relative position related to each other, carbon is down further. Germanium is down further than carbon. So therefore, we can expect for germanium to be larger. Okay. What about aluminum and nitrogen? Well, on the periodic table, going in this direction, we expect for this atom to be larger. But going down, we also expect it to be larger. And so therefore, it's clear cut that we can predict that going over to the right, to the left, we have an increase in size, and going down. So we can very easily predict that aluminum would be larger. The last one, that was an example that we used, was which one is larger, aluminum or germanium? Okay, on the periodic table, aluminum is located to the left of germanium. So that would indicate that it's a little bit smaller. A little bit larger than germanium. but it's also situated above germanium, which would predict that it's smaller. So going in this direction, we predict, okay, it's going to be larger. But now we take the same amount of distance upward, which tells us that it should be smaller, and those two cancel each other out. So we can't really predict based on the periodic table location alone which one is larger. Okay, because it's pretty clear that, okay, if we were just going one space over, we would expect it to be larger, but we're not just going one space over, we're also going one space up, which tells us, that should be smaller. So larger plus smaller cancels each other out. So we talked about in class that there's an exception to this, and that there's the transition metals always have something different going on with them. So generally, atoms in the same group increase in size down the column because of the larger amount of electrons that we add to the outer shell. But as we go across a period, for transition metals, their effective nuclear charge remains about the same. So therefore, there's not as much difference. There's a much less pronounced difference in the transition metals and across main group elements. We went into a lot of detail on this in class. We went into a lot more detail than we really needed for you to know. But what I really want you to carry away from this is that across a period for the transition metals, there's a whole lot less difference in size, and it's not as predictable. However, going down a family, we definitely still experience a larger atom as we go down in each period, as we go down the group. Okay. As we go down from period 1 to 2, I'm sorry, period 4 to 5 to 6 to 7, within each family, we experience a larger atom. But across the period, there's not as much difference. Just remember that. Okay. So that is, in a nutshell, how we can predict the trends in atomic size, how big an atom is based on its position on the periodic table. We can also do that for ions. But before we do, let us redefine what ions are and remind ourselves how we write electron configurations for ions. So, based on the position on the periodic table, we can pretty much predict what ions will form for the S block and the P block elements. So, when an atom increases its number of electrons, we know we form an anion. And when we decrease the number of electrons, we form a cation because we are removing positive charge. So we form a positively charged ion which is a cation. And over here, we're adding a negative charge. So we end up with a anion, which is more negatively charged. So we can predict for some elements which charges we can expect the element to form based on how its position on the periodic table and what it needs to do in order to look like this noble gas configuration. Everything wants to have 8 electrons in its outer shell. That's its strong desire. So in order to have 8 electrons in the outer shell, it is so much easier for the elements in this side of the periodic table to just lose an electron, and it can look like this. So elements in group 1A will lose 1 electron, so they generally form +1 cations. Elements in group 2 lose 2 electrons, so they generally form +2 cations. Elements on the right side of the periodic table, the nonmetals, aluminum is one exception. It likes to lose electrons to form, it likes to lose 3 electrons to form a +3 charge. The other ones, all of these nonmetals, we can predict with pretty good certainty what their charge will be. Nitrogen is in group 5. Its nearest noble gas is the easiest thing for it to do in order to get an electron configuration that has 8 electrons in its outer shell is to gain 3 electrons. And when it does that, it's going to have a -3 charge. You gotta use the plus sign interchangeably on the right or the left side. Things in group 6, the easiest thing for them to do to look like the noble gas, to have 8 electrons in its outer shell, is to gain 2 electrons. So therefore, it's going to have a -2 charge. And the things in the group 7 want to gain 1 electron, and therefore it will have a -1 charge. So we're adding 1 negative unit of charge here, 2 negatively charged particles here, 3 negatively charged particles here. So therefore, that's where we get our charge from. We're losing 3 negatively charged particles. So therefore, we end up with positive charges on these. When you lose an electron, you end up generating a charge on the atom that is equivalent to the amount of electrons that you lost. So how do we write electron configurations of cations in their ground state? So knowing that in order to form a cation, we must lose electrons. This is the electron configuration for magnesium. So magnesium has 2 valence electrons right here. In order to have magnesium in order for magnesium to have 8 valence electrons, it needs to lose these 2 here. And when it does that, it loses those 2 electrons. forming a magnesium 2 plus cation. This 2 plus simply means that these are the 2 electrons that were removed, and therefore we ended up generating a 2 plus charge. Similarly, for aluminum, this is just 2 separate ways of writing where the electrons are in aluminum. This is the orbital diagram here, and this is the electron configuration. Remember, when we remove electrons from an atom, we always remove them from the valence shell first before we start to remove them from the lower energy levels. So the valence shell for aluminum is 3p. I'm sorry, the valence shell for aluminum is 3. So energy level 3 has 2 electrons in the s orbital and 1 electron in the p orbital. So that's 3 total electrons. And in order to look like the noble gas configuration that it wants to look like, it loses those 3 electrons. And now it can look like neon. So this actually is the configuration for neon. So when something has the same number of electrons, we call it isoelectronic. So when something is a cation or an anion and it is a different number of protons, but it has the same number of electrons, we call it isoelectronic. So just to reiterate, in case I caused any confusion on this slide, in order to get the neon configuration, which is the nearest noble gas, which is 1s2, 2s2, 2p6, or simply to get 8 valence electrons in its outer shell, we need to remove 3 electrons. When we remove 3 electrons, we generate a aluminum cation that has a 3 plus charge on it, which actually has the same electron configuration as the nearest noble gas, which is neon. When we look at transition metals, we know that transition metals can form multiple charges. The metals that are in the S block and the P block that are not transition metals, we can easily predict what type of charge we expect them to have. But cation metals, transition metals can have various charges. So we can have an iron atom, for instance, that has either a +1, a +2, or +3 charge. And so when we actually remove electrons from transition metals in order to form their cations, we need to know that we need to remove them from the valence, from the outermost energy level first. So for instance, this is the iron atom here. And every time we remove 1 electron, we're going to increase its positive charge by 1. So going to a iron that has a 2 plus charge on it, that means we need to remove 2 electrons. So we can do that, but the first 2 electrons have to come from the 4s energy level. And this is the electron configuration that results. Then, if we need to remove any more electrons, let's say we want to go from an iron atom to a iron plus 3 cation, then we need to remove the electrons from the next energy level down next. So we need to remove 3 electrons to get a iron in the plus 3. So that means we need to remove 2 from here and then 1 from the D energy shell. And so when you do that, you end up with this electron configuration. And as you can see, there's no S electrons and the number of D electrons has decreased by 1. So this is the appropriate electron configuration for an iron plus 3 cation. When we have an electron configuration that results in unpaired electrons, then that atom or ion will have a magnetic field and it will be attracted to a magnetic field. And so we call those paramagnetic. And the effect is called paramagnetism. So basically, if in any orbital, if you have any number of unpaired electrons, you have paramagnetism, and we call this a paramagnetic ion or atom. On the other hand, if you have no unpaired electrons, it is not attracted to a magnetic field. As a matter of fact, it's slightly repelled by a magnetic field. We call that a diamagnetic atom or ion, and this effect is called diamagnetism. So remember that. Unpaired electrons give you paramagnetism. Paired electrons give you diamagnetism. Think about pair. So if cations are formed when we remove electrons, anions are formed when we gain electrons. And gain enough electrons to have 8 valence electrons. So basically we're going to be filling the S and P sublevels of the valence shell in order to achieve 8 valence electrons. So looking at sulfur as an example, the sulfur atom itself has this electron configuration. It has 16 total electrons. It is in group 6. So we can look at the periodic table and predict that it would need 2 extra electrons in order to have a complete outer shell of 8 electrons. But in order to completely fill that outer shell, which is the 3s and 3p, this is the outer shell. Looking at the diagram, in order to fill that outer shell, you need to add 2 electrons here, and that'll give us 3s2, 3p6 in the outer shell, which is what we want. So when we do that, this is what we end up with, and this is an S2 minus anion that results. So you have added 2 units of negative charge, which is 2 electrons. So ions are in the same group, of course, have the same charge. And just like the actual atom itself, the neutral atom, the ion size increases down a column and gets smaller as you go across the period. However, when you compare the atom itself to the cation or anion that forms from that atom, you get a difference in size. So looking at cations are smaller than their neutral atoms. Why? Because we have just removed electrons from around that atom, and so therefore its size has just decreased. So any cation is going to be smaller than its anion. And these are some examples, some explanations as to why, which is basically what I just told you. Um, the anions, on the other hand, are larger than the neutral atom. Because you are actually adding electrons on, so you're increasing their size. So, looking at some of the examples that we looked at in class, and telling you one last thing, if you have two atoms or what two ions that ions are atoms that two species that are have the same number of electrons but a different number of protons, then that means that they're isoelectronic. Then you should compare the number of protons, and the element that has the larger number of protons is going to be smaller in size, and that is because of the effective nuclear charge being higher. Okay, so if we compare sulfur or the sulfur ion, which one is larger? Well, sulfur, in order to become an ion, you have to add negative charge, add two electrons, so therefore the sulfur ion is larger. For calcium or calcium 2 plus? Well, for calcium, in order for calcium to go to 2 plus, we had to remove some of those outer electrons. So therefore, calcium is larger than its ion. The last one we looked at was bromine ion and krypton. Bromine ion has the same exact number of electrons in its outer cloud as krypton. So how can we tell which one is smaller? Well, we said if they're isoelectronic, if it has the same number of electrons, then we look at the number of protons to determine which one is larger. The one that has the largest number of protons is smaller. So therefore, bromine is larger in this case. Okay. And I think that this next couple of slides gives us some detail in why that is, why we expect the ions to be smaller than their neutral atom when they're positively charged and larger than their neutral atom when they're negatively charged. So that's where we stopped in class, and we'll be finishing chapter 8 on Tuesday and beginning chapter 9.